Scientists have discovered something terrifying about the speed of light. It's not that we can't reach it, it's that we shouldn't. Every time physicists push particles closer to this cosmic speed limit, they encounter the same chilling pattern. The universe isn't just making it difficult to reach light speed. It's protecting us from what we would become if we ever succeeded. Today we're diving into one of physics' most profound limitations. Why is it impossible to reach the speed of light? If you enjoy these kinds of cosmic mysteries, hit that subscribe button and give this video a like, because you just found the right channel. Now let's get started. The story begins over a century ago when a young patent clerk named Albert Einstein asked himself a deceptively simple question. What would happen if you could ride alongside a beam of light? This thought experiment would revolutionize our understanding of the universe and reveal why the cosmic speed limit of roughly 300,000 kilometers per second isn't just a big number. It's a fundamental boundary between possible and impossible. Let's start with something that might surprise you. Right now, as you're watching this, you're already traveling through spacetime at the speed of light. But here's the twist. Most of that motion is through time, not space. Einstein showed us that space and time aren't separate things but part of a four-dimensional fabric called spacetime. Everything in the universe is always moving through spacetime at exactly the speed of light. The faster you move through space, the slower you move through time, and vice versa. This isn't science fiction. It's been proven countless times. GPS satellites orbiting Earth have to account for time dilation, or they'd accumulate errors of about 10 kilometers per day. The International Space Station astronauts age slightly slower than people on Earth's surface. Even flying in a commercial airplane makes you age a tiny bit slower than someone on the ground. These effects are real, measurable, and they all stem from the same principle that makes light speed impossible to reach. As you accelerate through space, something remarkable happens to time itself. At 10% light speed, time dilation is barely noticeable. Clocks run about 0.5% slower. Push to 50% light speed, and time slows by about 15%. But as you approach light speed, the effect becomes dramatic. At 90% light speed, time passes less than half as fast. At 99%, time slows by a factor of 7. At 99.9%, the factor jumps to 22. The mathematics of relativity reveal an astonishing truth. As you get infinitesimally close to light speed, time dilation approaches infinity. If you could somehow reach exactly light speed, time would stop completely from your perspective. No thoughts could form, no processes could occur, no experiences could happen. You wouldn't just be frozen in time, you would exist outside of time itself. But time dilation is only part of the story. As you accelerate toward light speed, space itself begins to contract in your direction of motion. This length contraction, confirmed by particle physics experiments, means the entire universe would compress along your direction of travel. At 90% light speed, distances shrink to 44% of their original length. At 99.9%, the universe ahead of you would be compressed to just 4.5% of its normal depth. The energy requirements tell another part of this impossible story. Einstein's famous equation, E equals mc squared, reveals that mass and energy are interchangeable. As you accelerate, your kinetic energy increases, and from the perspective of a stationary observer, this manifests as an increase in your relativistic mass. The faster you go, the more massive you become, and the more energy it takes to accelerate further. Let's put this in perspective. To accelerate a single proton to 90% light speed requires about twice its rest mass energy. Push to 99%, and you need 7 times its rest energy. At 99.9%, the factor is 22. The pattern is clear and merciless. Each additional 9 after the decimal point requires exponentially more energy. The Large Hadron Collider, humanity's most powerful particle accelerator, consumes about 200 megawatts of power, enough to supply a city of 300,000 people. It uses superconducting magnets cooled to -271 degrees Celsius, creating magnetic fields 100,000 times stronger than Earth's. All this incredible technology accelerates protons to 99.999991% light speed. That's 7 nines after the decimal, and we still can't add those final decimal places. To accelerate something with the mass of a human to even 90% light speed would require more energy than the entire world produces in a year. To reach 99% would take thousands of times more. To reach 99.9% would require the energy output of a star. The energy needed for true light speed? Infinite. More energy than exists in the observable universe. But let's imagine, just for a moment, that you had access to infinite energy. Even then, the universe has other barriers in place. As you approach light speed, the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, would be blue-shifted to deadly gamma rays. Every hydrogen atom floating in interstellar space would impact your spacecraft with the force of a particle beam weapon. The gentle rain of cosmic rays would become a lethal storm of ultra-high energy particles. The visual effects alone would be mind-bending. Due to relativistic Doppler shift, the stars ahead of you would shift toward blue, then ultraviolet, then X-ray frequencies, becoming invisible to human eyes while simultaneously becoming deadly sources of radiation. Stars behind you would redshift into infrared and radio waves, disappearing from view. The entire visible universe would compress into an ever-shrinking circle of aberrated light directly ahead. This aberration effect, predicted by Einstein and confirmed by astronomical observations of fast-moving objects, would create a tunnel vision effect. At 90% light speed, your forward field of view would shrink to about 60 degrees. At 99%, it drops to about 25 degrees. Push to 99.9%, and you're looking through a narrow tunnel just 12 degrees wide. The universe itself would be telling you to stop. The quantum realm adds another layer of impossibility to light-speed travel that even Einstein couldn't have fully anticipated. When quantum mechanics emerged in the early 20th century, physicists discovered that the universe operates according to principles that seem to conspire against reaching light speed. The Heisenberg uncertainty principle states that you cannot simultaneously know both the exact position and momentum of a particle with perfect precision. As you approach light speed, where momentum approaches infinity, the uncertainty in position would have to approach zero, creating a quantum paradox that nature simply doesn't allow. Recent experiments at CERN have revealed something even more fascinating. When particles approach light speed in accelerators, they don't just gain mass, they interact with the quantum vacuum itself. Empty space isn't really empty. It seethes with virtual particles that pop into existence and annihilate in time frames shorter than the Planck time of 10 to the negative 43 seconds. These quantum fluctuations become increasingly important as you approach light speed, creating a kind of quantum friction that grows without bound. The discovery of the Higgs field in 2012 added another piece to this cosmic puzzle. The Higgs field permeates all of space, giving particles their mass through interaction with Higgs bosons. Think of it like cosmic molasses. Particles acquire mass by moving through this field. The faster you try to push through it, the more resistance you encounter. At light speed, this resistance would become infinite. Only particles that don't interact with the Higgs field, like photons, can travel at light speed precisely because they remain massless. But here's where things get truly strange. According to special relativity, if you could somehow reach light speed, you wouldn't experience any time passing at all. From your perspective, you would depart and arrive simultaneously, regardless of the distance traveled. A journey across the room, across the galaxy, or across the observable universe would all take exactly 0 time from your point of view. You would exist in a timeless state, frozen between moments, unable to think, perceive, or experience anything. This creates what physicists call the photon's paradox. Light itself travels at light speed, yet we receive information from distant stars and galaxies. How can photons carry information if they experience no time? The answer lies in understanding that photons exist in a fundamentally different way than massive particles. They don't experience reality as we do. They're created and absorbed in what, from their perspective, is the same instant, even if billions of years pass in our reference frame. The twin paradox, one of relativity's most famous thought experiments, becomes even more extreme when we consider actual light speed. Normally, the paradox describes how a twin traveling at high speed ages slower than their Earth-bound sibling, but at light speed, the traveling twin wouldn't age at all. They would return to find not just an aged sibling, but potentially a dead Earth, an extinguished sun, or even a universe approaching heat death, depending on how far they traveled. Recent observations from the James Webb Space Telescope have given us unprecedented views of the early universe, showing us galaxies as they existed over 13 billion years ago. These observations confirm that light speed has remained constant throughout cosmic history. If the speed of light had changed even slightly over billions of years, we would see distortions in these ancient galaxies that simply aren't there. The universe has maintained this cosmic speed limit with extraordinary precision since the beginning of time. The concept of simultaneity breaks down completely at light speed. Events that appear simultaneous to a stationary observer occur at different times for someone moving at high speed. At light speed, this effect becomes absolute. The entire history of the universe would collapse into a single moment. Birth and death, creation and destruction, the Big Bang, and the heat, death of the universe would all exist simultaneously in your frozen instant of travel. Particle physics experiments have revealed another barrier to light-speed travel, the strong nuclear force. This fundamental force holds atomic nuclei together, but it operates very differently at relativistic speeds. As particles approach light speed, the strong force can't propagate fast enough to maintain nuclear stability. Atoms would literally fall apart. The very matter that makes up your body would disintegrate into a soup of quarks and gluons, similar to the quark-gluon plasma that existed microseconds after the Big Bang. The weak nuclear force responsible for radioactive decay also behaves strangely at extreme velocities. Time dilation affects decay rates, as confirmed by observations of fast-moving muons created by cosmic rays. These muons live longer from our perspective because they're traveling at significant fractions of light speed. At true light speed, radioactive decay would stop entirely, freezing nuclear processes in an eternal moment. Even gravity, which we typically think of as the weakest fundamental force, becomes extreme near light speed. According to general relativity, mass warps spacetime, and moving mass creates additional gravitational effects. As your velocity approaches light speed and your relativistic mass approaches infinity, you would create gravitational distortions that would affect everything around you. You would become like a moving black hole, warping spacetime in ways that would make navigation impossible. The electromagnetic force presents perhaps the most intuitive barrier. As you accelerate charged particles toward light speed, they emit synchrotron radiation, light produced when charged particles are accelerated in curved paths. This radiation carries away energy, acting like a cosmic brake. The faster you go, the more energy you radiate away. At speeds approaching c, this radiation loss would become so severe that you'd need infinite power just to maintain constant velocity, let alone accelerate further. Recent discoveries in condensed matter physics have revealed materials called photonic crystals that can slow light to walking speed or even stop it entirely. But this isn't really stopping light itself. It's converting photons into other forms of energy that can be stored and released. True light always travels at c in vacuum. When it appears to slow down in materials, it's actually being absorbed and re-emitted by atoms, creating an effective slower speed. This shows us that even light itself cannot escape the universal speed limit. It must always travel at exactly c, never faster, never slower in empty space. The cosmic speed limit also shapes the large-scale structure of the universe. Because nothing can travel faster than light, there are regions of space we can never reach or even observe. The cosmic event horizon, caused by the accelerating expansion of space, means that galaxies beyond a certain distance are receding from us faster than light. Not because they're traveling through space faster than light, but because space itself is expanding between us. These galaxies are forever lost to us. Their light will never reach Earth, creating an island of observability in an infinite ocean of inaccessible space. Dark energy, the mysterious force driving cosmic acceleration, might be related to the vacuum energy allowed by quantum mechanics and constrained by light speed. The uncertainty principle permits virtual particles to briefly exist, borrowing energy from the vacuum as long as they annihilate quickly enough, a timeframe set by light speed. Some theories suggest dark energy emerges from this quantum foam, though calculations disagree with observations by 120 orders of magnitude, the worst prediction in physics history. The biological impossibility of light-speed travel reveals another dimension of nature's prohibition that goes beyond pure physics. Your body is a magnificent orchestration of chemical reactions, electrical signals, and molecular processes that all depend on precise timing. Neural signals travel through your nervous system at speeds ranging from 1 to 120 meters per second, glacially slow compared to light speed. At relativistic velocities, these biological processes would face insurmountable challenges that make life itself impossible. Consider what happens to your DNA at extreme speeds. This molecule, which carries the blueprint of your existence, maintains its double helix structure through hydrogen bonds and electromagnetic forces. As you approach light speed, relativistic effects would distort these bonds. The length contraction would compress your DNA along the direction of travel, while leaving it unchanged perpendicular to motion, literally tearing apart the molecular foundations of life. Every protein in your body would unfold, every cell membrane would rupture, every biochemical process would cease. Recent studies in astrobiology have shown that even the simplest organisms couldn't survive relativistic travel. Tardigrades, those microscopic water bears that can survive in the vacuum of space, extreme radiation, and temperatures near absolute zero, would still be destroyed by the effects of near-light-speed travel. The European Space Agency's experiments on the International Space Station have pushed organisms to their limits, but nothing in biology can withstand the infinite stresses that approach as velocity nears c. The consciousness problem becomes even more profound when we consider what neuroscience tells us about awareness. The global workspace theory suggests consciousness emerges from the integration of information across different brain regions. This integration requires time for signals to propagate, for patterns to form, for the dynamic interplay of billions of neurons to create the phenomenon we call thought. At light speed with time stopped, no integration could occur. Consciousness wouldn't just pause, it would cease to exist by definition. Quantum biology has revealed that consciousness might involve quantum processes in microtubules within neurons, as proposed by Penrose and Hameroff. These quantum effects are incredibly fragile, requiring careful isolation from environmental interference. The extreme energies involved in light-speed travel would instantly destroy any quantum coherence, eliminating any possibility of quantum consciousness. We wouldn't just lose classical neural activity, we'd lose any quantum aspects of awareness as well. The information-theoretic perspective adds another layer of impossibility. Claude Shannon's information theory tells us that information transmission requires time and energy. The Landauer principle demonstrates that erasing information generates heat, a fundamental connection between information and thermodynamics. At light speed, where no time passes, no information can be processed. Your thoughts, memories, and experiences are all forms of information processing. Without the ability to process information, you wouldn't just stop thinking. You would cease to exist as an information processing entity. But let's explore the hypothetical technologies people have proposed to approach or bypass the light-speed barrier. The Alcubierre warp drive, proposed in 1994, suggests warping spacetime itself rather than moving through it. By contracting space in front of a spacecraft and expanding it behind, you could surf a wave of distorted spacetime to your destination. The spacecraft never exceeds light speed locally, but the bubble of warped space can move arbitrarily fast. The energy requirements for an Alcubierre drive, however, are staggering beyond comprehension. Initial calculations required more than the mass energy equivalent of the entire observable universe. Refined calculations by physicists like Harold White have reduced this to roughly the mass energy of Jupiter, but that's still about 10 to the 27th kilograms converted entirely to energy. For comparison, the largest nuclear weapon ever detonated released energy equivalent to about 5 kilograms of matter. We'd need 10 billion trillion times more energy than that. Even more problematic, the Alcubierre drive requires exotic matter with negative energy density, something that might not exist in nature. While the Casimir effect demonstrates that negative energy densities can exist between conducting plates at quantum scales, scaling this up to macroscopic levels might be fundamentally impossible. The universe seems to have a positive energy conjecture that prevents the large-scale negative energy densities needed for warp drives. Traversable wormholes offer another theoretical loophole, creating shortcuts through spacetime that could allow effective faster-than-light travel without actually exceeding c locally. These Einstein-Rosen bridges, as they're formally known, are valid solutions to Einstein's field equations, but naturally occurring wormholes, if they exist, would collapse instantly. Faster than light could traverse them. Keeping one open would require threading it with exotic matter possessing negative energy density, the same impossibility that plagues warp drives. Recent work in quantum gravity has suggested even more exotic possibilities. String theory's extra dimensions might allow shortcuts through higher dimensional space. Brainworld scenarios propose that our three-dimensional space is a membrane floating in a higher dimensional bulk. Perhaps gravity can leak into these extra dimensions, allowing forms of communication or travel impossible in our familiar four-dimensional spacetime. But even these speculative theories maintain that nothing can exceed light speed in its local spacetime. The cosmic speed limit remains absolute. The tachyon hypothesis proposes particles that always travel faster than light, never slower. If tachyons existed, they would have imaginary mass and experience time backward from our perspective. But decades of searches have found no evidence for tachyons, and their existence would create causality paradoxes. You could send messages into your own past, creating grandfather paradox scenarios where you could prevent your own existence. The universe seems to forbid such logical contradictions. The many worlds interpretation of quantum mechanics offers a different perspective on faster-than-light travel. In this view, every quantum event branches the universe into parallel realities. Some physicists have speculated that consciousness might be able to navigate between these parallel worlds, achieving effective faster-than-light travel by taking paths through the multiverse. But this remains pure speculation, with no experimental evidence or even a coherent theoretical framework. Quantum entanglement initially seemed to offer hope for faster-than-light communication. When particles are entangled, measuring one instantly affects the other regardless of distance. Einstein called this spooky action at a distance and used it to argue that quantum mechanics must be incomplete. But experiments have confirmed that while entanglement creates instantaneous correlations, it cannot transmit information faster than light. The no-communication theorem proves that quantum mechanics preserves causality despite its non-local features. The holographic principle, emerging from black hole thermodynamics, suggests that our three-dimensional reality might be encoded on a two-dimensional boundary. Some theorists speculate that this could allow forms of travel that bypass three-dimensional distance limitations. But even in holographic theories, information cannot propagate across the boundary faster than light. The cosmic speed limit appears to be fundamental to the structure of reality itself, not just a feature of our particular dimensional setup. Recent observations of neutron star mergers have provided natural experiments in extreme physics. When two neutron stars collide, they create conditions approaching the theoretical limits of matter and energy density. The LIGO and Virgo gravitational wave detectors observed these mergers, confirming that gravity itself propagates at exactly the speed of light. This observation ruled out many alternative theories of gravity and reinforced the universality of the cosmic speed limit. The philosophical implications of the light-speed barrier touch the very heart of what it means to exist in our universe. We're not just talking about a technical limitation on how fast we can travel. We're confronting a fundamental boundary between being and non-being, between existence as we understand it and something utterly alien to conscious experience. The speed of light isn't merely the universe's speed limit, it's the rate at which causality itself propagates through the cosmos, the maximum speed at which causes can create effects. Consider what this means for free will and determinism. In a universe where influences could propagate instantly, where faster-than-light travel was possible, the entire concept of cause and effect would break down. You could receive a message before it was sent, arrive at your destination before you left, even prevent your own birth through time travel paradoxes. The light speed limit preserves the logical structure of reality, ensuring that causes always precede effects, that time flows in a consistent direction, that the universe maintains a coherent narrative structure. The anthropic principle, the observation that the universe's physical constants seem fine-tuned for the existence of conscious observers, takes on new meaning when we consider the speed of light. If light traveled infinitely fast, electromagnetic forces would propagate instantaneously, preventing the formation of stable atoms. If light traveled much slower, stellar fusion would proceed differently, possibly preventing the creation of heavy elements necessary for planets and life. The specific value of c appears optimized for a universe capable of producing complexity and consciousness. Recent discoveries in neuroscience have revealed that consciousness itself might depend on the finite speed of neural signals. The binding problem, how separate brain regions processing different aspects of experience combine into unified consciousness, requires precise timing of neural oscillations. Gamma waves around 40 Hz seem particularly important for conscious awareness. These oscillations depend on signals propagating at specific speeds through neural tissue. Infinite signal speed would prevent the formation of these crucial rhythms, making consciousness as we know it impossible. The integrated information theory of consciousness, developed by Giulio Tononi, provides a mathematical framework for understanding why awareness requires time. Consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. This integration requires causal connections between different parts of the system, connections that must unfold through time. At light speed, where no time passes, integrated information drops to exactly zero. Consciousness doesn't just stop, it becomes mathematically undefined. But the impossibility goes deeper than biology or information theory. The very structure of spacetime conspires against light-speed travel for conscious beings. General relativity shows us that spacetime is a dynamic, flexible fabric that responds to matter and energy. As you approach light speed, you're not just moving through spacetime, you're fundamentally altering its geometry around you. The infinite energy required to reach c would create infinite spacetime curvature, essentially forming a black hole around the would-be traveler. The Unruh effect adds another layer to this cosmic prohibition. Discovered by physicist William Unruh, this effect shows that accelerating observers experience a thermal bath of particles even in empty space. The faster you accelerate, the hotter this quantum thermal bath becomes. As you approach the accelerations needed for light speed, this temperature approaches infinity. You would be immersed in a quantum inferno, bombarded by an infinite flux of particles created by your own motion through the quantum vacuum. Recent experiments with ultra-intense laser fields have begun to probe these extreme quantum effects. The extreme light infrastructure in Europe can create electric fields approaching the Schwinger limit, where the quantum vacuum itself breaks down and produces particle-antiparticle pairs. These experiments give us a glimpse of the violent quantum processes that would make light speed travel impossible, even if we could somehow provide infinite energy. The connection between entropy and the arrow of time provides another perspective on why consciousness cannot exist at light speed. The second law of thermodynamics states that entropy, disorder, always increases in isolated systems. This entropic arrow gives time its direction and makes memory possible. We remember the past, but not the future, because the past had lower entropy. At light speed, where no time passes, entropy cannot change. Without increasing entropy, no memories can form, no experiences can accumulate, no learning can occur. String theory, our best candidate for a theory of quantum gravity, suggests that the universe has more than the 4 dimensions we experience. These extra dimensions might be compactified, rolled up so small we can't detect them, or we might be confined to a 4-dimensional brain in a higher dimensional space. Some theorists have speculated that these extra dimensions might allow shortcuts that bypass the light speed limit. But even in 10 or 11-dimensional string theory, nothing can exceed light speed in its local reference frame. The cosmic speed limit transcends dimensionality. The ADS-CFT correspondence, one of the most profound discoveries in theoretical physics, reveals deep connections between gravity, quantum mechanics, and information. This duality suggests that gravitational physics in a volume of space is exactly equivalent to quantum physics on the boundary of that space. From this holographic perspective, trying to exceed light speed in the bulk would be equivalent to trying to violate causality on the boundary, something the mathematics simply doesn't allow. Loop quantum gravity, another approach to quantizing spacetime, suggests that space itself is discrete at the Planck scale of 10 to the negative 35 meters. In this picture, spacetime is like a fabric woven from tiny loops of quantized geometry. The speed of light emerges as the maximum rate at which changes can propagate through this quantum fabric. Trying to exceed c would be like trying to make a wave travel faster through a material than the material structure allows. Not just difficult, but definitionally impossible. The cosmic censorship hypothesis proposed by Roger Penrose suggests that nature abhors naked singularities, points where physics breaks down in ways visible to outside observers. Black holes hide their singularities behind event horizons, preventing the breakdown of physics from affecting the outside universe. The light speed barrier might serve a similar protective function, preventing conscious observers from reaching states where the laws of physics cease to make sense. Recent observations of the cosmic web, the largest structure in the universe, have revealed that even on scales of billions of light-years, the speed of light shapes cosmic evolution. Galaxy clusters are connected by filaments of dark matter and gas, with voids between them. The finite speed of light means that gravitational influences take time to propagate, allowing these structures to form and evolve. An infinite light speed would create a universe of instantaneous interactions, preventing the gradual assembly of cosmic structure we observe. The discovery of dark energy has added another dimension to our understanding of cosmic speed limits. The accelerating expansion of space means that distant galaxies are receding from us at ever-increasing rates. Galaxies beyond the cosmic event horizon are already receding faster than light, not because they're moving through space faster than c, but because space itself is expanding between us. This creates a fundamental limit on how much of the universe we can ever explore, even if we could travel at light speed. The quantum mechanical nature of reality reveals even deeper reasons why consciousness and light speed are fundamentally incompatible. When we dive into the quantum realm, we discover that the universe operates according to principles that seem specifically designed to prevent massive objects from reaching c. The wave-particle duality, confirmed in countless experiments from the double-slit to modern quantum interference tests with large molecules, shows that all matter has wave-like properties. As you approach light speed, your de Broglie wavelength, the quantum wavelength associated with your motion, shrinks toward zero. At exactly c, this wavelength would vanish entirely, meaning you would cease to exist as a quantum mechanical entity. The quantum Zeno effect provides another barrier that emerges from the fundamental structure of quantum mechanics. This effect, demonstrated in numerous laboratory experiments, shows that frequent observation can freeze a quantum system's evolution. A watched quantum pot never boils, as physicists say. As you approach light speed, the universe itself becomes the observer, with every interaction with the quantum vacuum effectively measuring your state billions of times per second. This cosmic observation would lock you into an increasingly frozen state, preventing the dynamic evolution necessary for consciousness. Recent breakthroughs in understanding quantum decoherence shed light on why macroscopic objects face even greater challenges approaching light speed than individual particles. Decoherence occurs when quantum systems interact with their environment, causing superposition states to collapse into classical behavior. The rate of decoherence increases dramatically with object size and energy. A human-sized object approaching light speed would decohere so rapidly that maintaining any coherent quantum state, potentially necessary for consciousness, would be impossible. The vacuum catastrophe, one of the greatest unsolved problems in physics, connects directly to the impossibility of light-speed travel. Quantum field theory predicts that empty space should contain enormous energy from virtual particle fluctuations, roughly 10 to the 120 times more than we observe. This discrepancy between theory and observation suggests we're missing something fundamental about the quantum vacuum. Whatever resolves this catastrophe might also explain why the vacuum itself resists the passage of massive objects at light speed. Experiments with Bose-Einstein condensates have revealed states of matter that exist only near absolute zero, where quantum effects dominate over thermal motion. These condensates can slow light to walking speed, or even stop it entirely by converting photons into collective excitations of the condensate. But this isn't truly stopping light. It's converting electromagnetic energy into matter excitations and back. The fundamental speed of light in vacuum remains inviolate. These experiments show us that even in the most extreme quantum states, the cosmic speed limit cannot be violated. The measurement problem in quantum mechanics, how and why quantum superpositions collapse into definite states, becomes acute when considering light speed travel. Some interpretations suggest consciousness plays a role in wave function collapse. But if consciousness cannot exist at light speed due to the freezing of time, who or what would collapse the wave function of a light speed traveler? This creates a paradox that might be nature's way of preventing such situations from arising. Recent discoveries in quantum information theory have revealed fundamental limits on how quickly information can be processed. The Margolis-Levitin theorem sets a maximum rate for quantum state transitions based on available energy. As you approach light speed, where infinite energy would be required, this theorem suggests that information processing would slow to zero. Since consciousness appears to be a form of information processing, this provides another independent proof of its impossibility at sea. The black hole information paradox offers insights into what happens to information at extreme conditions. When matter falls into a black hole, the information it carries seems to vanish, violating quantum mechanics' requirement that information be preserved. Recent theoretical advances suggest the information is preserved in subtle quantum correlations. A conscious being approaching light speed would face a similar information crisis. Where would the information constituting their thoughts and memories go as time freezes? Quantum tunneling, the phenomenon that allows particles to pass through barriers they classically shouldn't be able to cross, might seem to offer hope for bypassing the light speed barrier. After all, tunneling appears to be instantaneous. But careful experiments have shown that tunneling time, while very short, is not zero. More importantly, the probability of tunneling decreases exponentially with particle mass. For a macroscopic object, the probability of tunneling to light speed is so small, it might as well be zero. The cosmic speed limit also shapes the quantum vacuum in ways we're only beginning to understand. The Casimir effect demonstrates that parallel conducting plates experience an attractive force due to the restriction of vacuum fluctuations between them. This shows that the quantum vacuum is a real, physical thing that can exert forces. As objects approach light speed, their interaction with this quantum vacuum becomes increasingly violent, creating a kind of cosmic friction that grows without bound. Recent experiments with ultra-cold atoms have created artificial event horizons, boundaries beyond which phonons, sound waves, cannot escape, analogous to black hole event horizons for light. These analog systems allow us to study horizon physics in the laboratory. They've confirmed that horizons are real, physical boundaries where the nature of space-time changes fundamentally. The light-speed barrier represents another kind of horizon, one that separates the realm of massive objects from the realm of massless radiation. The holographic principle emerges from studying black hole thermodynamics and suggests that all the information in a volume of space can be encoded on its boundary. This principle might explain why three-dimensional beings cannot reach the two-dimensional boundary represented by light speed. We are volumetric information patterns that cannot be compressed onto the null surface that light inhabits without losing everything that makes us conscious entities. Quantum chromodynamics, the theory of the strong nuclear force, reveals another barrier to light-speed travel. This force, which binds quarks into protons and neutrons, behaves very differently at high energies. As particles approach light speed, the strong force creates quark-gluon plasma, a state where normal nuclear matter breaks down entirely. The Large Hadron Collider has created tiny regions of this plasma, confirming that normal atoms cannot survive the conditions approaching C. The weak nuclear force, responsible for radioactive decay and stellar fusion, also conspires against light-speed travel. Beta decay rates are affected by time dilation, as confirmed by observations of cosmic ray muons. At light speed, where time stops, all weak force processes would freeze. This would prevent the nuclear reactions that power stars, the radioactive decays that heat planetary interiors, and the particle interactions that might be necessary for consciousness. Even the electromagnetic force, the most familiar of nature's fundamental forces, becomes exotic near light speed. Synchrotron radiation, light emitted by accelerating charged particles, increases dramatically with velocity. Particle accelerators must constantly pump energy into circulating beams just to compensate for synchrotron losses. At speeds approaching c, this radiation would become so intense that maintaining velocity would require infinite power. The cosmological implications of the light-speed barrier extend far beyond individual travelers to shape the entire evolution and ultimate fate of our universe. The finite speed of light creates what cosmologists call the particle horizon, the boundary of the observable universe beyond which we cannot see, because light hasn't had time to reach us since the Big Bang. This horizon expands at the speed of light, but due to cosmic expansion, there are regions of space we will never observe, no matter how long we wait. The universe has built-in limits to knowledge, enforced by the same cosmic speed limit that prevents us from reaching c. Dark matter, which makes up about 27% of the universe's energy content, might hold clues to the deeper meaning of the light speed limit. We know dark matter exists through its gravitational effects on galaxies and cosmic structure, but it doesn't interact electromagnetically. Some theories propose dark matter particles that barely interact with normal matter at all. Could there be an entire dark sector of physics with its own forces and particles, all respecting the same universal speed limit? The fact that even invisible, barely interacting dark matter cannot exceed CE suggests this limit is more fundamental than any particular force or interaction. The inflationary epoch, that brief moment of exponential expansion in the universe's first fraction of a second, seems to violate the light speed limit. During inflation, regions of space separated faster than light could travel between them. But this isn't a true violation. Space itself was expanding, carrying regions apart, without any object moving through space faster than c. This distinction between motion through space and the expansion of space itself reveals the subtle nature of the cosmic speed limit. You cannot travel through space faster than light, but space itself follows different rules. Recent observations of Type Ia supernovae, which led to the Nobel Prize-winning discovery of cosmic acceleration, have revealed that the expansion of space is speeding up. Dark energy, whatever it is pushing galaxies apart at an ever-increasing rate. In the far future, all galaxies beyond our local group will pass beyond the cosmic event horizon, receding faster than light due to spatial expansion. The finite speed of light, combined with accelerating expansion, condemns the universe to increasing isolation and darkness. The cosmic microwave background, that ancient light from when the universe first became transparent 380,000 years after the Big Bang, provides our deepest look into cosmic history. This radiation has been traveling at light speed for over 13 billion years, carrying information about the universe's infancy. The patterns in this radiation, mapped by satellites like Planck and WMAP, reveal quantum fluctuations stretched to cosmic scales by inflation. These tiny variations seeded all cosmic structure, galaxies, stars, planets, and ultimately life itself. But the CMB also reveals the universe's ultimate fate. As cosmic expansion continues, this radiation will be redshifted to ever longer wavelengths, eventually becoming undetectable. Future civilizations, billions of years from now, will have no direct evidence of the Big Bang. The finite speed of light means that evidence of cosmic history is constantly passing beyond our observational horizon, lost forever to the expansion of space. Gravitational waves, ripples in spacetime itself predicted by Einstein and finally detected by LIGO in 2015, travel at exactly the speed of light. The observation of gravitational waves from merging neutron stars, which arrived at Earth simultaneously with electromagnetic radiation from the same event, confirmed this to extraordinary precision. This observation ruled out many alternative theories of gravity and reinforced that C is truly universal. Not just the speed of light, but the speed of causality itself, the rate at which any influence can propagate through spacetime. The multiverse hypothesis, emerging from eternal inflation and string theory, suggests our observable universe might be one bubble in an infinite foam of universes. Each universe might have different physical constants, different laws of physics. But theoretical work suggests that universes permitting complex structures and observers would likely need something like our light speed limit. Without a finite maximum speed for causal influences, it's difficult to see how any universe could develop the kind of structured complexity necessary for consciousness to emerge. Black holes provide natural laboratories for studying what happens when spacetime is pushed to its limits. At the event horizon, the escape velocity equals the speed of light. Inside, all paths lead inexorably to the central singularity. Time and space effectively switch roles. The singularity becomes as inevitable as tomorrow. Recent observations of material falling into black holes confirm that nothing, not even light, can escape once it crosses the horizon. These cosmic monsters enforce the ultimate speed limit with absolute authority. The information paradox associated with black holes connects to deep questions about the nature of reality. If information falling into a black hole is destroyed when the black hole evaporates through Hawking radiation, it would violate quantum mechanics. Recent theoretical advances suggest information is preserved, perhaps encoded in subtle correlations in the radiation. This preservation of information, even in the most extreme conditions, might be telling us something profound about why conscious beings cannot reach light speed. The information constituting consciousness must be preserved, and this preservation is impossible at sea. Wormholes, those hypothetical shortcuts through spacetime, would seem to offer a way around the light speed limit. But every theoretical investigation has found that traversable wormholes require exotic matter with negative energy density to stay open. The universe seems to have a deep aversion to such exotic matter on macroscopic scales. Even if wormholes exist, they might be quantum fluctuations at the Planck scale, far too small and brief for any conscious being to traverse. The chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics conspire to prevent time travel and its associated paradoxes. Whenever a scenario might allow closed time-like curves, paths through spacetime that loop back to their own past, quantum effects build up to destroy the would-be time machine. The light speed limit is part of this cosmic censorship, preventing the superluminal travel that could lead to causality violations. Recent studies of quantum gravity effects in the early universe have revealed that space-time itself might become fundamentally different at extreme energies. Loop quantum cosmology suggests that the Big Bang singularity is replaced by a quantum bounce, where the universe transitions from contraction to expansion. These quantum geometry effects only become important at the Planck scale, but they hint that our familiar notions of space and time are emergent properties that break down under extreme conditions, including the approach to light speed. The possibility of extra dimensions, suggested by string theory, adds layers of complexity to the light speed limit. In theories with large extra dimensions, gravity might propagate through the bulk, while other forces are confined to our four-dimensional brain. This could explain why gravity is so much weaker than other forces. But even in these exotic scenarios, nothing can exceed the speed of light in its local spacetime. The cosmic speed limit transcends dimensionality. Observations of the most distant galaxies by the James Webb Space Telescope are revealing surprises about early cosmic history. Some galaxies appear more massive and mature than expected for their age, suggesting that structure formation proceeded more rapidly than our models predicted. But these observations still respect the light speed limit. We see these galaxies as they were billions of years ago, their light having traveled at CI across cosmic time to reach our instruments. The search for loopholes in the cosmic speed limit has driven some of the most creative thinking in theoretical physics. Yet every investigation has only reinforced how fundamental this barrier truly is. Quantum entanglement, once hailed as spooky action at a distance by Einstein himself, initially seemed to violate the prohibition on faster-than-light influences. When entangled particles are measured, they show perfect correlations regardless of the distance separating them. Modern experiments have confirmed these correlations across distances of hundreds of kilometers, with some satellite experiments planning to test entanglement across thousands of kilometers. But the no-communication theorem, proven mathematically within the framework of quantum mechanics, shows that entanglement cannot be used to send information faster than light. The correlations are real, but they're like a cosmic conspiracy that preserves causality. You can't use entanglement to send a message because the results appear random at each location. Only when compared later do the correlations become apparent. Nature has built in a safeguard that allows quantum non-locality while preserving the causal structure of spacetime. The delayed choice quantum eraser experiments push this mystery even further. These experiments seem to show that future measurements can affect past quantum states. But careful analysis reveals that no information travels backward in time. The universe maintains consistency through subtle quantum correlations that respect causality even while challenging our intuitions about the nature of time and measurement. It's as if the cosmos has multiple layers of protection against causality violations. Tachyons, hypothetical particles that always travel faster than light, have captured imaginations since they were first proposed in the 1960s. If they existed, tachyons would have imaginary mass and experience time flowing backward. But every experimental search has come up empty. Moreover, tachyon theories face severe theoretical problems. They would enable communication with the past, creating grandfather paradoxes. Most physicists now believe tachyons are mathematical curiosities rather than physical possibilities, another way the universe says no to faster-than-light travel. The Alcubierre drives seem to offer a legitimate loophole by warping spacetime rather than moving through it. By contracting space ahead and expanding it behind, a spacecraft could surf a wave of distorted spacetime. The mathematics checks out within general relativity, but the devil is in the details. Recent calculations show that quantum effects would destroy any would-be warp bubble. Hawking radiation at the bubble's horizons would incinerate anything inside. The universe closes this loophole through quantum mechanics, even if general relativity alone might allow it. Attempts to use rotating black holes as cosmic shortcuts face similar quantum roadblocks. The Kerr metric describes rotating black holes with ring-shaped singularities that might be traversable. Some solutions even suggest passages to other universes or distant regions of our own. But quantum effects near the inner horizon of rotating black holes create what's called a mass inflation instability. Any attempt to traverse the black hole would trigger an exponential buildup of energy that destroys the would-be passage. Once again, quantum mechanics steps in to preserve causality. The vacuum energy of empty space provides another angle on why light speed is inviolable. Quantum field theory predicts that empty space seethes with virtual particles constantly appearing and disappearing. This quantum foam becomes increasingly violent at higher energies. As you approach light speed, your interaction with the quantum vacuum would release cascades of real particles from the virtual sea. It's like trying to move through an increasingly dense medium that ultimately becomes impenetrable at sea. Recent experiments with metamaterials, artificially structured materials with properties not found in nature, have created media where light appears to travel backward or faster than c. But these are phase velocity effects, not true superluminal motion. No information or energy actually exceeds light speed. These experiments actually confirm the universality of the cosmic speed limit by showing that even exotic engineered materials cannot violate it for actual signal transmission. The cosmic censorship hypothesis extends beyond black holes to any situation where physics might break down. Roger Penrose suggested that nature abhors naked singularities, places where the laws of physics fail in view of outside observers. The light speed limit might be the ultimate cosmic censor, preventing conscious observers from ever reaching regimes where known physics fails. It's as if the universe protects its own consistency by making such states unreachable. Studies of ultra-high-energy cosmic rays have revealed another enforcement mechanism for the cosmic speed limit. The GZK cutoff occurs because protons with energies above about 5 × 10 to the 19 electron volts interact with the cosmic microwave background, losing energy to particle production. This creates a universal speed limit even for the highest energy particles in nature. The universe itself provides a cosmic brake that prevents anything from approaching too close to c. The relationship between complexity and the speed of light reveals deep connections. Complex systems require time to evolve, feedback loops to develop, and information to flow between components. The finite speed of light ensures that complexity can emerge gradually rather than instantaneously. Without this speed limit, the universe might collapse into a state of maximum entropy instantly, preventing the slow development of structure that led to galaxies, stars, planets, and life. Quantum computing research has uncovered fundamental limits on information processing that connect to the light-speed barrier. The Margolis-Levitin theorem shows that the maximum rate of quantum operations depends on available energy. As you approach light speed, where infinite energy would be required, the rate of quantum operations would paradoxically approach zero. This suggests that consciousness, if it involves quantum computation, faces fundamental limits as velocity increases. The holographic bound, emerging from black hole thermodynamics, sets maximum limits on information content in any region of space. This bound depends on area rather than volume, suggesting that reality might be fundamentally two-dimensional. As objects approach light speed, they must respect this holographic bound, which becomes increasingly restrictive. The information content required for consciousness might simply not fit within the constraints imposed by relativistic compression. Recent observations of fast radio bursts, mysterious millisecond pulses from distant galaxies, have tested whether different frequencies of light travel at different speeds across cosmic distances. The results confirm that all electromagnetic radiation, regardless of frequency, travels at exactly c in vacuum. This universality across the entire electromagnetic spectrum reinforces that the speed of light is a fundamental property of spacetime itself, not just a peculiarity of visible light. The connection between entropy and information provides another perspective on the light speed barrier. The second law of thermodynamics requires entropy to increase, but this increase requires time. At light speed, where time stops, entropy cannot change. Since consciousness seems to require increasing entropy, memories form, experiences accumulate, learning occurs, the frozen entropy of light speed travel precludes awareness. The universe's thermodynamic arrow of time is incompatible with existence at c. String theory's landscape of possible universes suggests that different regions of a larger multiverse might have different physical constants, but studies of which constants allow complex structures show that some version of a cosmic speed limit appears necessary. Universes without a finite maximum speed for causal propagation tend to be either boringly simple or chaotically unstable. Our universe's specific value of c might be selected by anthropic considerations. We observe this value because other values don't permit observers. The emergence of consciousness from unconscious matter represents one of the universe's most remarkable phase transitions, and this emergence appears to be fundamentally incompatible with light speed existence. Consciousness isn't just a collection of neural firings or quantum processes. It's an emergent phenomenon that arises from the complex interplay of billions of components over time. This emergence requires what complexity theorists call downward causation, where higher-level patterns influence lower-level components. At light speed, where time freezes, no such emergence can occur. Recent advances in complexity science have revealed that consciousness might be understood as a critical phenomenon, similar to phase transitions in physics. Just as water suddenly becomes ice at 0 degrees Celsius, consciousness might emerge when neural complexity crosses a critical threshold. But critical phenomena require time to develop, fluctuations to grow, and feedback loops to establish themselves. The frozen time of light speed travel would prevent any critical transition from occurring, making consciousness impossible by definition. The global workspace theory of consciousness, developed by Bernard Bars and refined by Stanislas Dehaene, suggests that awareness arises when information becomes globally accessible across different brain regions. This global broadcasting requires time for signals to propagate, for competition between neural coalitions to resolve, and for winning information to spread throughout the brain. At light speed, this temporal orchestration would cease entirely. Consciousness wouldn't just pause, it would become structurally impossible. Integrated information theory provides a mathematical framework for understanding why consciousness requires time. Developed by Giulio Tononi, this theory proposes that consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. The mathematics shows that integration requires causal connections that unfold through time. At light speed, where causes cannot produce effects, integrated information drops to exactly zero. Consciousness becomes not just absent, but mathematically undefined. The hard problem of consciousness, explaining how subjective experience arises from objective physical processes, becomes even harder when we consider light-speed travel. David Chalmers's formulation of this problem highlights the explanatory gap between neural activity and conscious experience. But whatever bridges this gap, it must involve processes that unfold through time. The quale of experiencing red, the feeling of pain, the sense of self, all of these subjective phenomena require temporal duration. At light speed, subjectivity itself would vanish. Recent discoveries in quantum biology suggest that consciousness might involve quantum coherence in microtubules within neurons, as proposed by Roger Penrose and Stuart Hameroff. These quantum effects are incredibly fragile, requiring isolation from environmental decoherence. The extreme energies and field strengths involved in approaching light speed would instantly destroy any quantum coherence. Even if consciousness has quantum aspects, they would be obliterated long before reaching C. The binding problem in neuroscience: how the brain combines separate sensory inputs into unified perceptions, reveals another temporal requirement for consciousness. When you see a red ball bouncing, your brain must bind together color, shape, motion, and location information processed in different regions. This binding requires precise timing of neural oscillations, particularly gamma waves around 40 Hz. At light speed, these oscillations would freeze, making unified perception impossible. The predictive processing theory of consciousness suggests that awareness arises from the brain's constant generation and updating of models about the world. This requires comparing predictions with sensory input, updating models when predictions fail, and generating new predictions for the future. All of these processes require time. Time for predictions to be generated, for sensory data to arrive, for comparisons to be made. At light speed, predictive processing would halt entirely. Memory, fundamental to consciousness, depends on the arrow of time established by increasing entropy. We remember the past but not the future because information flows from low entropy past states to high entropy future states. This thermodynamic arrow gives time its direction and makes experience possible. At light speed, where entropy cannot change, the distinction between past and future disappears. Without this distinction, memory becomes meaningless, and without memory, consciousness, as we understand it, cannot exist. The attention schema theory, proposed by Michael Graziano, suggests that consciousness is the brain's model of its own attention processes. This metacognitive awareness requires the brain to monitor its own states, compare them with goals, and adjust attention accordingly. These monitoring and adjustment processes require time to unfold. At light speed, the brain couldn't model its own attention because attention itself would be frozen in time. Recent studies of altered states of consciousness provide insights into how temporal perception affects awareness. Psychedelic experiences often involve distortions of time perception, with users reporting that minutes feel like hours or that time stops entirely. But even in these extreme states, some temporal flow continues. Thoughts still progress, experiences still unfold. True temporal cessation, as would occur at light speed, appears incompatible with any form of conscious experience. The default mode network, a set of brain regions active during rest and introspection, shows how consciousness requires ongoing neural activity. This network, discovered through neuroimaging studies, maintains a baseline level of activity even when we're not focused on external tasks. It's associated with self-referential thinking, mind-wandering, and the sense of self. At light speed, this network would freeze, eliminating the neural basis for self-awareness. Anesthesia research reveals how consciousness depends on the integration of information across brain regions. General anesthetics don't just reduce neural activity, they disrupt communication between different brain areas. Consciousness fades as integration decreases. At light speed, integration would drop to zero as no signals could propagate between brain regions. The result would be deeper than any anesthesia, a complete absence of awareness. The phenomenon of blind sight, where people with damaged visual cortex can respond to visual stimuli they claim not to see, illustrates the difference between unconscious processing and conscious awareness. Blind sight patients can navigate obstacles and identify emotions in faces they insist they cannot see. This suggests that consciousness requires something beyond mere information processing. It requires the temporal integration that creates unified, reportable experience. At light speed, even unconscious processing would cease. Studies of split-brain patients whose corpus callosum has been severed to treat epilepsy reveal how consciousness depends on communication between brain hemispheres. These patients sometimes show conflicting behaviors between their left and right hands, suggesting that unified consciousness requires ongoing communication across the brain. At light speed, this communication would stop, potentially fragmenting consciousness, even if some form of awareness could somehow persist. The neural correlates of consciousness, the specific brain activities associated with conscious experience, All involve dynamic processes that unfold over time. Whether it's the gamma oscillations that bind perceptions together, the global ignition that makes information conscious, or the recurrent processing that creates rich phenomenology, all require temporal duration. The frozen time of light-speed travel would eliminate every known neural correlate of consciousness. Recent advances in artificial intelligence have begun to create systems that exhibit some aspects of consciousness-like behavior. But even the most sophisticated AI systems require time to process information, update their models, and generate responses. The temporal requirements for artificial consciousness mirror those for biological consciousness, suggesting that the need for time is fundamental to any form of awareness, not just biological forms. The cosmic perspective on consciousness and light speed reveals something profound about the universe's architecture. We exist in a cosmos where the same physical laws that govern stellar fusion and galactic rotation also make consciousness possible. The speed of light isn't just a barrier to travel, it's a fundamental organizing principle that creates the temporal scaffolding necessary for awareness to emerge from matter. Without this cosmic speed limit, the universe would be a very different place, one where the slow, patient processes that led to stars, planets, and life could never have occurred. Consider how stellar evolution depends on the finite speed of light. Nuclear fusion in stellar cores produces photons that take thousands of years to random walk their way to the surface. This slow energy transport allows stars to burn steadily for billions of years rather than exploding instantly. If light traveled infinitely fast, stellar energy would escape immediately, preventing the long-lived stable stars necessary for planetary systems and life. The same speed limit that prevents us from reaching CE also makes our Sun possible. The formation of complex elements in stellar cores and supernovae requires precise timing of nuclear processes. The triple alpha process that creates carbon from helium, the S process that builds heavy elements through slow neutron capture, the R process that forges gold and platinum in neutron star mergers, all depend on reaction rates governed by the fundamental constants of physics, including the speed of light. Change C, and you change the entire periodic table, potentially making the chemistry of life impossible. Galaxy formation itself depends on the light speed limit. Dark matter halos collapse under gravity, while ordinary matter cools by radiating photons. This cooling process, essential for star formation, requires photons to escape at exactly the speed of light. Too fast, and matter couldn't cool efficiently. Too slow, and radiation pressure would prevent collapse. The precise value of C appears fine-tuned for a universe capable of creating the cosmic structures we observe. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, carries information about the universe's infancy precisely because it has been traveling at light speed for over 13 billion years. The tiny temperature fluctuations in this radiation, mapped by satellites like Planck, reveal the quantum fluctuations that seeded all cosmic structure. These fluctuations were stretched to cosmic scales by inflation, but their subsequent evolution depended on the finite speed of light to create the causal horizons that shaped structure formation. Recent observations of the most distant galaxies by the James Webb Space Telescope show us cosmic history laid out in space. Because light takes time to travel, we see these galaxies as they were billions of years ago. This cosmic archaeology is only possible because of the finite speed of light. In a universe with infinite light speed, we would see everything as it is now, losing access to the cosmic past that tells us how the universe evolved. The anthropic principle takes on new meaning when we consider consciousness and light speed together. Not only are the fundamental constants fine-tuned for the existence of atoms, stars, and planets, but they're also fine-tuned for the emergence of consciousness. The speed of light creates the temporal structure necessary for complex information processing, while also preventing conscious beings from reaching states where consciousness becomes impossible. It's as if the universe is designed to permit awareness while protecting it from its own destruction. Quantum mechanics adds another layer to this cosmic fine-tuning. The uncertainty principle, which emerges from the wave nature of matter, requires a finite speed for the propagation of information. If influences could propagate infinitely fast, the uncertainty principle would break down, eliminating the quantum effects that might be necessary for consciousness. The delicate balance between classical and quantum physics that makes complex chemistry possible depends on the same speed limit that prevents light speed travel. The arrow of time, established by the second law of thermodynamics, gives the universe its narrative structure. Entropy increases, creating a distinction between past and future that makes memory, learning, and experience possible. This thermodynamic arrow is intimately connected to the speed of light through the propagation of causal influences. Without a finite speed limit, the careful balance between order and disorder that allows complexity to emerge would be impossible to maintain. Recent studies of complexity and emergence have revealed that the most interesting phenomena occur at the edge of chaos, the boundary between order and disorder. Life, consciousness, and intelligence all seem to emerge in this critical regime. The finite speed of light helps maintain this edge by preventing instantaneous global interactions that would either freeze the system in perfect order or drive it to complete chaos. The cosmic speed limit creates the conditions where complexity can flourish. The search for extraterrestrial intelligence takes on new meaning when we consider the universal nature of the light-speed barrier. Any conscious beings anywhere in the universe would face the same fundamental limitations we do. They cannot travel at light speed, cannot send information faster than c, and cannot escape the temporal requirements for consciousness. This creates a kind of cosmic democracy where all conscious beings, regardless of their technological advancement, must respect the same physical laws. The Fermi paradox, the puzzling absence of obvious signs of alien civilizations, despite the vast number of potentially habitable worlds, might be partially explained by the light-speed barrier. Even highly advanced civilizations cannot exceed c, limiting their ability to colonize the galaxy rapidly. The vast distances between stars, combined with the impossibility of light-speed travel, might keep civilizations isolated from each other, explaining why we haven't encountered obvious signs of alien intelligence. But the light-speed barrier also offers hope for the long-term survival of consciousness in the universe. As cosmic expansion accelerates and galaxies recede beyond the cosmic event horizon, isolated regions of space will become increasingly cut off from each other. The finite speed of light, which prevents us from traveling to distant galaxies, also prevents the heat death of the universe from occurring instantaneously. Local regions can maintain complexity and potentially consciousness long after the universe as a whole has reached maximum entropy. The ultimate fate of consciousness in an expanding universe depends on the same physics that makes light-speed travel impossible. As space expands and cools, the energy available for computation decreases. But the finite speed of light means this process occurs gradually, potentially allowing consciousness to adapt and survive by becoming more efficient. The cosmic speed limit that constrains us today might be what allows awareness to persist into the far future. Recent theoretical work on digital physics suggests that the universe itself might be computational, with reality emerging from information processing at the Planck scale. If true, the speed of light might represent the maximum clock speed of the cosmic computer, the fundamental rate at which reality updates itself. Consciousness would then be a pattern of information processing that must respect the same computational limits that govern all of physics. The holographic principle, emerging from black hole thermodynamics and string theory, suggests that our three-dimensional reality might be encoded on a two-dimensional boundary. From this perspective, the light-speed barrier might represent the boundary between the volumetric world we experience and the holographic surface where information is actually stored. Conscious beings, as three-dimensional information patterns, cannot cross into the two-dimensional realm of light without losing their essential structure. The impossibility of light-speed travel connects us to the deepest mysteries of existence. Why does the universe have the particular set of physical constants it does? Why do these constants permit the emergence of complexity and consciousness? Why does reality have the structure it does with space and time, matter and energy, all governed by mathematical laws that conscious beings can discover and understand? These questions push us toward what physicists call the anthropic principle, the observation that the universe's properties seem remarkably well suited for the existence of observers. Some interpret this as evidence of design, others as a selection effect in a multiverse where only observer-compatible universes can be observed. But regardless of interpretation, the light-speed barrier stands as one of the most striking examples of how the universe's fundamental structure enables rather than constrains the emergence of consciousness. Recent discoveries in cosmology have revealed that we live in a universe dominated by dark energy, a mysterious force causing cosmic expansion to accelerate. In the far future, this acceleration will carry distant galaxies beyond our cosmic horizon, making them forever inaccessible even to light-speed travel. The universe is becoming increasingly isolated, with islands of matter separated by ever-growing voids. Yet this same process that limits our cosmic reach also ensures that local regions can maintain complexity and consciousness long after the universe as a whole approaches maximum entropy. The search for a theory of quantum gravity, a unified description of the very large and very small, continues to reveal new aspects of the light-speed barrier. Whether through string theory's extra dimensions, loop quantum gravity's discrete spacetime, or other approaches, every attempt to understand reality's deepest level confirms that the speed of light represents something fundamental about the structure of existence itself. It's not just a speed limit, but an organizing principle that shapes everything from quantum mechanics to cosmic evolution. The possibility of artificial intelligence achieving consciousness raises new questions about the universality of the light-speed barrier. If consciousness can emerge from silicon and software as well as carbon and chemistry, it would still face the same temporal requirements we've explored. Any form of awareness, biological or artificial, requires time for information processing, memory formation, and the integration that creates unified experience. The light-speed barrier would constrain artificial consciousness just as it constrains biological consciousness. As we stand on the threshold of becoming a spacefaring civilization, the impossibility of light-speed travel might seem like a cosmic disappointment. The stars appear tantalizingly close in the night sky, yet they remain separated by distances that would take thousands of human lifetimes to cross even at significant fractions of light speed. But perhaps this limitation is exactly what makes the universe interesting. A cosmos where any destination could be reached instantly would be a very different place, one where mystery, exploration, and the gradual accumulation of knowledge would be impossible. The light-speed barrier preserves the universe's capacity for surprise. It ensures that there are always new horizons to explore, new questions to ask, new mysteries to unravel. It creates the temporal structure that makes stories possible, including the story of how the universe evolved from simplicity to complexity, from unconsciousness to awareness, from a hot, dense plasma to a cosmos capable of contemplating its own existence. And what if you could travel at 1 light-year per second? Check out the video on the screen to find out. In this mind-expanding journey, we imagine what you'd see if you could make the impossible possible and soar beyond physics through the deepest reaches of space, compressing the history of the universe into moments. It's a must-watch.